stream just keeps on ending. Uh, I don't know. It's a little bit annoying, but we're back at it. We're going till 2:30. Going till 2:15 to be exact. So let's go. Let's get lost in the sauce and go ahead and work for about, let's see, 55 minutes, it seems. 50 minutes, actually. Yep. All right. So let's go. Let's take this quiz and see if we can kill it. Come on, man. What happened? There you go. Oh, Zoom. All right. So we want a T that represents this right here. So we can reason it out in our head. Let's try. So we have a 3 by 1. That means we want a 2 by 3. 2 by 3 here. So either of these. And we could just think about the matrix multiplication. So it looks like with this one, you get x1 plus 3x2. That is not the case here. It's the case here. So for this one, you can see that you get x1, which is this, minus this one. The matrix during matrix defining the transformation is, okay, let's see, same question. So this one is going to be it's a 2 by 1, so we're going to get a 3 by 2. 3 by 2, either one of these guys. So without looking at these answers, it's going to be 1 and negative 1. And this one's going to be 2 times x plus 1 times y. Consider the following functions. Select all the functions that are linear transformations. Yep. So there are some rules that we can follow with this, and they are laid out in a document I have. It's one of these. One of these things. Quadratic form. It can be less than 6, is it? It is. Look at this. All right. So you can very well reason out uh, if the property of addition works, uh, right? It may not. So, um, for example, uh, you can try x1, y1, z1, x2, y2, and z2. And you'll see that individually you get 0 and z1, then you get 0 and z2. You'll see that if you add them together, you get the same thing as uh, you get the same result if you add the vectors and then apply the transformation as if you do the transformation on both of them and then add the, the, the results. And the same thing with multiplication. A quicker way to do this is you can really just eyeball these. And let me tell you how. This is quadratic. It's a function times a function. This has a constant in it. So, I don't know, it's not cool. This looks pretty chill, and this has some, cosine function a part of it, so that's not too. Which of the following defines a linear mapping? So let's see. How can you figure this one out? Well, not one. Definitely not one for this, because if you try and add two results together, you're gonna get two. You're gonna get twice this. It's just a constant, so that has to be 0. Um, uh, Good morning, sir. Um, keep up. No, it's needed. So it's got to be 0 here. This one could low-key be. Does it matter? I feel like it just doesn't matter. Ooh, yes it does. Yes it does. This one's got to be 0 to get rid of this quadratic. Ooh, yeah. Too easy. Oh, shit. What is this question? A linear transformation satisfies T1 more T. Well, I have to really kind of draw this out. So matrix T 1 1 goes to 0 negative 1, and matrix T with 2 negative 1 goes to matrix 3 2, which the following is given by that. Well, T has to be a 2 by 2 for this to work. So we can easily assume. Ooh, I remember how we did this. This was like wait, I think I did. All right, check me out. Check me out. Check me out. Yeah, this is a cool ass problem. So let's see. We know one times A plus one times B equals 0. We know what's the word for both? Negative one could work. One and negative one could work. Now we just have to put it on to we can have, so it has to be 1 times A plus 1 times B equals negative 1, and also 2 times A plus negative 1 times B equals 2. And so we turn this into a little matrix here, a little system of solutions, and we cancel that out. So negative 2 minus 2 is negative 3. 2 minus minus 2 is 4. And so then we turn this into that. And then we get rid of this guy right here with 0. And we turn negative 1 minus minus 4, 3. So plus 4, 3. So that's just 1/3. So we find the solution here. AKA, now we can solve this out. We would have 1 and negative 1, so we would have 3 on top. And negative 4, let's see. Wait. Ah, negative 4, baby. Yeah, that's an awesome problem. That is such an interesting. Let's see if you're right. This was good. This was good. Yo, am I stupid? Am I dumb? Why did I put all of them? This is good. What do you mean? It was negative 3. It was negative 3 and negative 4. Yeah. All right. Next quiz. Go over to the next quiz. I feel like we're going to get a B in the class, which is not too sexy, but maybe we can clutch and get an A. Maybe. Let's go. So it looks like I could do this one. Let A, all right, let's see. You know what I want to wait. You know what I want to do actually. Okay, we'll do this and then we'll do this little experiment I have. So this quiz is intended to help you with the concepts of the four fundamental subspaces. Got you. All right. So rank three. So the 3 by 5. Sure. Rank three. Pick all the correct statements. The rows of A are linearly independent. The left null space A. Oh, shit. That's right. These properties down. You can get your butt right over there. I'll do this. You can chill right here. You chill it. All right. So let's see. Let me rank up three. What's it? So the uh, four fundamental subspaces. So let's go over to the four fundamental subspaces. Get the properties. Oh, it gets two-sided. I'm kind of good. All right. So I'm pretty sure the left null space is what's it called, orthogonal to the column space. So we don't really have to know that. It's right here. Yeah, so we know that. What we don't know really is the dimension of A of the column space of A equal to the dimension of the row space of A. That was not obvious to me. The dimension of the null space is equal to, I think, the number of rows minus R. Let's see. Is the left null space equal to the is the dimension of the left null space equal to the number of rows minus rank? Yeah. In this book, rows is fucking n for some reason. Psych alive with n. Number of calls. Cool. All right. The left null space is the rows, which is 3 here, minus 2, minus, wait, rows minus rank. I guess it should be 0. That's 2. I don't know. Has to be good. necessarily. I don't think so. I don't think so. Nullity of A equals n minus the dimension. So dimension. That's equal to the rank, buddy. So n is the number of columns. So yeah, that's that. The nullity of A is the number of non-fitted columns. The nullity of A is the number of non-fitted columns. RREF. Really? I guess so, because it's n minus the rank, and the rank is the number of fitted columns. I guess so. Nullity of A is the same as the nullity of this guy. I don't think so, but the nullity of A is the number of linearly independent columns in A. The number of A is the number of linearly independent columns in A. Yo, no way. I'm going to get the rest of it. Oh, this guy didn't even chat or anything to the good. Ooh, hey, hey, don't look at that. Hey, I didn't see that. We're going to practice that at another point in time. Where did the bell, where did it go? Exam. Modules, let's go to YouTube. Imagine we get 100 points. All right, anyway, let's keep going on this quiz. So the nullity of A is the same as the nullity of AT. Nope, the nullity of A is the same as the, no, the nullity, no, the nullity of A is the number of non-zero rows. That's a tricky one. Yeah. Kind of. in certain cases, Consider the echelon form of the matrix A. I'm looking to consult our buddy here. And I'm thinking in the case that we just saw, yeah, the number of non-zero rows is going to be 0. But if we think about the dimension of the left null space and non-column, and wait. What am I talking about? Consider the echelon form of matrix A, given by this the correct statement. Um, so basically, find the four fundamental subspaces. Well, it'd be good to practice that right now, actually. Let's see. So, we're going to do 0, 2 minus, we're going to do this row minus that row times 2. It's going to be 3 plus that, which is going to be 5. Okay, so the column space is these two, which are the row space is going to be these two, which is it's this, or if it's after the root after the REF. We're gonna think that maybe it could be before the REF. The left null space. Hold on. Why the hell is it here? So how do you get the null space again? Well, we can think about the set of vectors that this matrix brings to 0, but Fourth and 6. All right, I'm gonna say no. Oh my gosh, bro! You can quickly find the general solution of the REF to get the recognition. Now I forget how to get the general solution or something. Good, Nelson. Good. Good, buddy. 5. Okay, 0, 5, 1, wait, no, -1, and -1. Plus, that's it. Right? Or it could be this as well, right? Uh, it could be that as well, right? Because the dimension of the null space is going to be what? The number of rows for -2. So it can not have that vector, or it can include this guy here. So that could work as well. Now, I'm confused on how to find the left null space. How do you Okay, I could do that, honestly. Alright, fuck it. I'm just gonna do it the long way. I'm not gonna use orthogonality ideas. Rows turn to columns. 0, 1, 0, 5, 0, 0, 1, -1, 0, 0, 0, 0. So I mean, you can just cancel these out and switch these. So literally, the number of rows, which is 3, minus the rate. Probably. I just don't know why. Consider the matrix A. Consider the matrix A and its echelon form U. Pick all the correct statements from below. Okay, what is echelon? I know, like we're just doing that. However,